So our warm-up today is practicing the nomenclature that we just covered yesterday in regards to benzene. So I want you to draw orthodibromobenzene, and I want you to try and provide the name for this other compound. And then once you're done, I have a comment about one of the molecules that we covered yesterday. Ralph, do you feel like you've got it?
The first one, for sure.
Yeah? And the second one you feel?
Wait, I just forgot the aldehyde name.
Yeah, you would actually just remove the E at the end of benzene, or actually everything after the Z, benzaldehyde. However, if you call it 1-nitro-benzaldehyde, that kind of implies you're calling it benzaldehyde, so you're referencing it based on the aldehyde group. Yeah. And then if you call it 1-nitro, you're kind of saying that the nitro and the aldehyde group are in the same position. What would you go with, Caesar? Para.
Right. Does it matter then which was 1 and which was 4?
If you call it para,
no.
Neither of them are 1 or 4.
Oh.
They're just 1, 4 to each other. But because that compound really is best named benzaldehyde, there's no other way to make the aldehyde a good substituent and then call it benzene. The only other way to name it would be 4-nitro-benzaldehyde. So because you're naming it benzaldehyde, the aldehyde is always at 1. But really, like, nothing has to be 1 or the other. So you're on the right track, and you've added in that suffix that indicates the aldehyde, but benzene's a little bit different. Benzene, we'll call it benzaldehyde. It feels clunky, yeah, but that's what we look for. I would choose one of these two. So rather than saying para-4-nitro, the para implies that the nitro is 4 to the benzaldehyde. So either one of those would be just as effective. Perfect. And I didn't actually take a look at your drawing of the first ones. That looks great. Yep. Nailed it. Got it. That one was easy, huh? So, the O stands for ortho, which is what position? What relational position? 1, 2. We've got 2 different ways we could name this bottom structure. The root for the compound is going to be named off of the aldehyde because there's no easy way to make the aldehyde a substituent of the benzene. So we'll name the compound as benzaldehyde. And one of you went with just benzal. Not a bad idea because that is how we change the suffix for every other compound that has an aldehyde, but benzene's a bit out of the ordinary. Benzaldehyde. Now we want to reference the nitro group, and we need to be specific about its placement, and there are 2 ways to do this. Because I've named the compound benzaldehyde, I have assumed that this is position 1, which means that I could either call this 4-nitrobenzaldehyde. I don't have to explicitly say that the aldehyde is at position 1. That's implied. Or I can call it para-nitrobenzaldehyde because it's got that 1-4 relationship. We wouldn't name it both para-4-nitro. Up here we could call this 1,2-dibromo instead of ortho. In the event that you want to use the numbers instead of the descriptor, and you've got two different groups. So let me give you guys another example. Sorry, I'm going to make this one meta. So let's say you wanted to do, you wanted to name this, and you weren't sure if you wanted to use the descriptive names or the numbers. The nice thing about using the descriptor, I don't know why I keep saying it's para, meta, now I don't need to say which one is position 1 and which one is position 3. I know by saying meta that they are positions 1 and 3. So then I can just name the groups and alphabetize them. So this becomes meta, hydroxy, methyl, benzene. And there's a lot of other variations for that too. Can you guys give me another way that I could name this meta something? Think about using common names instead of systematic names.
One starts with a T.
One starts with a T. Meta, hydroxy. Do you guys remember? Toluene. So I'm referencing the methyl group making the compound toluene and the alcohol group meta to that methyl group. What's another way that I could name this? With another common name. Phenol? So meta, methyl, phenol. Now I'm referencing that the hydroxy group is at position 1, the methyl group is meta to it. And again, in all of these, with these two, I could replace meta with 3. I could call this 3-hydroxytoluene or 3-methylphenol. I can't really do that up here. If I wanted to use numbers up here, I would have to place a number for each of the substituents. And then how would I decide which one goes first? Well, because the substituents are being listed alphabetically, I'm going to prioritize their locants alphabetically. 1-hydroxy, 3-methylbenzene. And you can see that this, I don't know, I like that name the least because it clutters it up more, it elongates it. It's not as necessary. Either of these, though, would be great. Now, yesterday somebody had that comment, which was, when you've got the phenol, shouldn't it be called benzenol? Because we've got cyclopentanol and butanol. Benzenol, kind of similar to what we saw today with somebody trying to call this benzal. And I said, no, we don't take the suffix like we normally do and just plop it on the end. But actually, you have this bonus homework assignment, and one of the compounds it wants you to draw names itself 2-methylbenzenol. I've never seen the alcohol suffix applied to benzene in that way outside of this compound. But then you can see down here, there's a molecule 2-hydroxybenzaldehyde rather than 2-hydroxybenzenal. So I'm not sure how common that is, but I will tell you that for my class, you're going to see either phenol, which I think implies pretty well that there's an alcohol group on a phenyl structure, or you'll see hydroxy. Ideally, probably something more systematic like this. Where we left off yesterday was looking at di-substituted compounds. I want to take a second to look at polysubstituted benzenes. These terms that we've used, ortho, meta, and para, can only be applied to di-substituted benzene structures. once we move into polysubstituted groups, we're going to name it in such a way that we can minimize minimize the numbering pattern. Minimize the locant set. And then what's interesting is how the name changes from systematic to common. So here I've got a tri-substituted benzene. And this is actually a molecule that we're going to learn how to synthesize in the next week. We'll look at reactions that could take us from benzene directly to a compound like this. So first, let's look at the systematic name, the IUPAC name. IUPAC says that none of these groups are highest priority, and so I really can just number in such a way that minimizes the locant set. So that means I'll start here at bromine, and I'll number through to the other bromine, or vice versa. And that's going to give me a locant set of 1, 2, and 3. And then in the nomenclature, bromine gets placed alphabetically ahead of methyl. So I get 1,3-dibromo, 2-methylbenzene. Seem fair? Follows our normal rules. If you were to apply a common name to this structure, you'd identify that methyl group and name the benzene structure toluene, referencing that methyl group. This now becomes position 1, because you have established that the methyl group creates or transforms benzene into toluene. So where the methyl group is automatically becomes position 1. So what is the locant set that can be given to the bromines then? Not 1 and 5? 2 and 6. So here's position 1. The next position would be position 2, and then I'd have to go all the way around the ring back to position 6.
You said the common names were not that important. Are we going to be testing on it like that?
I want you guys to be familiar, but I do my best not to give you a common name and require you to know it. But it is useful to be familiar with it, because a lot of the resources you'll go and look at, they'll lean into those common names a lot more. So on graded questions, systematic names always accepted, and systematic names are preferentially given to you. But there might be bonus problems, or there might be parts of the question that talk about a different name. Okay, so 2,6-dibromo toluene. Interesting how the locant set flips on its head when something happens like that. Okay, let's do just one more, and I'll have you guys draw it based on its name. Three hydroxy, 4-chlorobenzoic acid. Would it be wrong to name this compound meta-hydroxy-para-chlorobenzoic acid? It would be wrong. The idea could be communicated, but IUPAC system says you can't use orthometapara outside of a dye-substituted compound. And it looks like this is dye-substituted, hydroxy and chloro. But it is tri-substituted as evidence of benzoic acid. It's not just benzene. It's got that carboxylic acid substituent. Anybody feel brave enough to come in and put it on the board?
Could try.
Yeah, let's see.
I don't know if it's right, but I can try.
Very good. Was it important where Caitlin put the benzoic acid? Not at all. Totally up to you on what position you want to start at. But after that, we have to make sure that the alcohol group gets placed meta to it and that the chlorine gets placed para to it. So notice how you can still use those descriptive terms to indicate the relationship between two groups. You just can't put it in the nomenclature. Chlorine is para to the benzoic acid. The alcohol is meta to the benzoic acid. And the chlorine and the alcohol are ortho to each other. I don't have to go through the jargon of saying they're 1,4 to each other, 1,3 to each other. We can use those terms when looking at a polysubstituted compound. We just can't put it into the nomenclature. Okay. One last thing I want to talk about with nomenclature of aromatic rings before we move on, which is this reagent. Do you guys remember this? Do you remember what it stands for? Do you remember what it does?
Does it make an epoxide?
Reacts with alkenes to make an epoxide. So there is an oxygen in that compound that is easily donated to an alkene, and that oxygen is what forms the epoxide ring. The compound name is meta-chloroperoxybenzoic acid. So you've now come full circle with this reagent. You might not necessarily know what a peroxy acid is, but if you know what a peroxide is, an oxygen-oxygen single bond, all you have to do is make that benzoic acid a peroxy acid. You have to add an OO single bond, place the chlorine meta to it. Now you understand the structure of MCPBA, not just what it is. And after it reacts, it produces a compound called, oh, sorry, I thought I saw it up here. Yeah, meta-chlorobenzoic acid. That peroxy oxygen gets donated in the addition reaction. Cool? It's fun to get it to take a look back at things that you just memorized in OChem 1, and now you can actually interpret their structure a little bit more. Okay. I do want to point out that there are many, many other aromatic rings, especially polysubstituted aromatic rings. We are not going, polycyclic, not polysubstituted, polycyclic aromatic rings. We're not going to spend any time on them. So you don't need to feel like this is something you need to copy down, but if you are interested in polycyclic aromatics, then this is something you can dig into more. You'll notice that I've got what looks like 2 benzene rings fused together and then 3 benzene rings fused together. There is another structure that has 3 benzene rings fused together, except they are fused at kind of this offset angle. And these give us aromatic compounds called naphthalene, anthrene, and phenanthrene. You guys will actually notice that on the homepage of our course, there is a chemical reaction shown. And that chemical reaction starts with a phenanthrene derivative. It's a dibromo diketone phenanthrene derivative that gets cyclized into a macrocycle. It's 3 equivalences of phenanthrene where the bromine-bromine bonds are removed, the carbon-bromine bonds are removed, and those carbons get coupled to one another. And just as much as the starting material is aromatic, the intermediate here is predicted to be aromatic. And then you can see there's a reaction that converts this ketone into an amine group, and it recovers the aromaticity of the phenanthrene, completely recovers the aromaticity in it. This was a reaction sequence that I proposed in my first year of graduate school. This was going to be a target of my PhD dissertation. It cost about $300 to get half a gram of this starting material. And so we did 2 reactions, one that started with 1/4 of a gram of that starting material, trying to cyclize it. And the product, being such a large molecule, it's not easily dissolved in any solvent. So it's a really challenging reaction to run. And we used this catalyst, nickel cod, which is cyclooctadiene. Very cool organic-inorganic interaction between the nickel d orbitals and the pi electrons of cyclooctadiene. Ultimately, I didn't run the second set of the reaction. It scared me too much. Like $150 for this 1/4 of a gram to try and run it and not even know if it was actually working because it's hard to dissolve it. And then I left my PhD to come teach. So I think it was a good push. You know, it's an interesting structure, and it gives me some perspective on the chemistry that we're talking about. But it is a challenge to be the one that is proposing research and carrying it out. It's also extremely expensive. Anyways, I digress. Let's move on. Let's actually talk about some other reactions around benzene, ones that we're going to be using quite a bit this semester. So these are not reactions with benzene, but these are reactions supported by benzene. So we're going to call these benzylic reactions. Just to clarify, this is benzene, but any of these carbons would be considered phenyl carbons, or probably more generally aryl carbons, meaning that they're aromatic or they're arenes. So then where is the benzylic carbon, if not within benzene? You guys know this.
All of them?
All of them?
So part of the benzene.
Mm-mm. No, the ones that are part of the benzene ring are considered aryl carbons. This one, adjacent to benzene, is benzylic. And this one out here, the one that's not directly attached, doesn't have a name. That's nothing. So when we talk about benzylic reactions, we're talking about reactions that occur adjacent to the benzene ring. So not things that are changing the benzene ring, but things that are mediated by the benzene ring, stabilized by the benzene ring. So I want to start with a review because there's a good chance that some of you have already seen some of this. I like to call these previously, before we introduce anything that might be new. Now, I understand some of you may or may not have seen these reactions. Maybe none of you have, but the reagents for sure will be very familiar. First, let's look at radical halogenation. When a benzylic carbon reacts with either Br2 or NBS in the presence of ultraviolet light, which is what we're denoting there with H nu, a radical carbon intermediate is formed. And that radical intermediate forms on the most stable position. In this case, the most stable position is the benzylic position. Now, I'm not going to take us through the mechanism because this isn't a mechanism that we're going to need to know how to use or that we'll need to show, but I do want to show you the intermediate. Here's this benzylic radical. And this benzylic radical is in resonance. It's conjugated with the aromatic ring. So that radical can move around through the aromatic ring. It can be at these positions, ortho and para, to the benzylic position that's going through the reaction. Now, I think some of you know how stable is a radical. Not stable. Highly reactive. And so it's not easy to form radicals either. It requires quite a bit of energy to create that highly reactive intermediate. So the easiest way to make a radical is to form a radical that is at the lowest energy, the most stable radical. And by delocalizing that radical electron, you are stabilizing it. You're essentially taking its reactivity and dispersing it across several atoms. Then it reacts with another equivalence of Br, or a bromine radical. And there is something interesting to be said here, right? Which is, my radical forms on the benzylic position. That's where the hydrogen is removed. If a hydrogen had been removed from the aromatic ring, it wouldn't have been in resonance. There would have had no way to participate in conjugation. Think about molecular orbitals. We could demonstrate using molecular orbital theory that the orbital this radical would form in cannot participate in conjugation, but this radical can. But then why doesn't the radical react from any of these three positions within the ring? The radical will only ever react with the bromine at the benzylic position. So the radical is delocalized through the ring, but it never reacts within the ring. The radical only ever reacts at that benzylic position. This actually is an indicator to us that aromaticity, something about this six-membered ring with the alternating double bonds, is incredibly energetically favorable. A reaction might take advantage of conjugation, but it's not going to break that aromatic ring. So I want to give you guys another example to apply this. what can we predict to be the major product of this radical halogenation? So you'll notice now that there's not just one benzylic position. There are two. And those two benzylic positions are related how to each other? Ortho, meta, or para? Not para. Ortho. They're 1-2 relationship. Do you know, I don't really have a good way of recognizing, connecting ortho to 1-2, para to 1-4. So if you guys think of a good way to make them make sense rather than just memorizing them, I'm all ears. You got a question though?
No, it was like a spatial thing for some reason that bus 21-2 was
Were you looking at maybe this?
Yeah, I was looking at that, yeah.
I see.
I don't know.
So you guys see there's two rings, but only one of them is the benzene ring. This other ring is just alkane structure. So there are two benzylic positions. There's one here, and there's one here. Which means we could probably predict two major products. Now the reason I've given you this structure is because in OChem 1, when you likely learned this reaction, one thing that we looked for was placing the bromine at the most substituted position. Here, there is a tertiary carbon. The more substituted the carbon, the more stable the radical, unless that radical can be in conjugation. Conjugation stabilizes the radical far more than just being more substituted. So in OChem 1, you likely would have looked for that tertiary carbon and placed the bromine there. But now that we have our aromatic ring providing this radical stabilization, we can predict two major products. And although it's beyond the scope of our class, we could probably predict which of these products is more major and which of these products is more minor. Because we just reviewed that typically the bromine prefers to go to a more substituted carbon. That radical then is kind of shielded from reacting, which makes it more stable. And although these are both secondary carbons, they're both carbons bonded to two other carbons, this carbon is adjacent to a tertiary carbon, which makes its surroundings more substituted. So this would probably be a more major product, but given that they are both benzylic, you'll likely produce both of them. Questions on the radical substitution? Okay. The other ones that you've probably seen are substitution and elimination reactions. There's not much to be said here. There's not a lot of difference in doing these substitution and elimination reactions, other than the pi electrons, the pi system of the aromatic ring, can speed up these reactions. So it makes these reactions faster and more favorable. There is something I want to show you about this as well. So what we'll do is we'll have two bromines. One bromine is an aryl bromine. It's connected directly to the ring. The other bromine is a benzylic bromine. And we'll react this with cyanide. Weak base, but a strong nucleophile. Something that is ready to share its electrons. the aromatic ring cannot go through SN2 reactions. So that aryl bromine stays where it is. Never reacts. And instead, the benzylic bromine goes through the reaction.
Did you say why it doesn't?
We, in our next section, so right now we're in section 15 talking about aromaticity. In section 16, we're going to look at reactions on the aromatic ring. We will be able to do substitution reactions on the ring, but not SN1 and not SN2. Instead, we call them SNAR for aromatic. But also, we'll do SEAR, electrophilic substitution of the aromatic ring. But we'll also call these EAS and NAS reactions. So just to draw your attention to this again, no SN2 on the aryl halide. Let's do another similar one where we look at dehydration of an alcohol. And we'll recognize that a phenol cannot go through dehydration because it's not favorable to form a triple bond within that ring. Not that it's impossible to form a triple bond within the aromatic ring. You can form a triple bond within the aromatic ring. It creates a compound called Benzene. It's just incredibly explosive and hard to synthesize.
So even have also like beta hydrogen, right?
There is a beta hydrogen, right? Here and here.
Oh, but not like for the.
But it would be incredibly energetically demanding to remove that beta hydrogen and the OH and to form a triple bond. Because we can recognize there's already a double bond between those two carbons. So forming a triple bond would take a lot of energy. Not easy to do. Doesn't happen preferentially. Okay, good review? Great. Let's move on from previously and look at some new reactions. A surprising reaction that we'll see is oxidative cleavage. Let's take toluene again as our base reaction, and I'm going to show you that there are two reagent routes that we can take that actually end up getting us the same product. So this reaction is going to take us from toluene to benzoic acid. I want to make a point here. I don't like when reaction names don't explain what's going on. I'm actually not sure that oxidative cleavage highlights itself well in this example. So we're going to do another example that highlights oxidative cleavage better. Because cleavage kind of implies cutting something off. And this just looks like oxidation without anything being lost. You can see that the carbon is preserved. It's just being oxidized. Its hydrogens are removed. I also don't like reactions or reagents that are named after people. So any chance that I can to avoid using somebody's name, I will. And there are instances it's just really challenging to. So some of you may be familiar with Jones reagent. Anybody heard that term before? Okay, so a couple of us, mainly the people from other institutions. Jones reagent, named after a guy named Jones. What is it? What does it do? It doesn't imply anything. There are two ways to do this oxidation reaction. One of them uses chromic acid. And there are a lot of different ways that you will see chromic acid written. In my class, you'll see chromic acid written as chromium trioxide with sulfuric acid. Tunotice that there isn't actually chromic acid in the reagent. Chromic acid is H2CrO4. The mixing, though, of chromium trioxide with sulfuric acid generates chromic acid in situ. And there are other ways that you can see this written. Sometimes you'll see this written as maybe sodium chromate plus acid, or maybe you'll see this as potassium dichromate plus acid. All three of those reagents are different ways of giving us H2CrO4 chromic acid. Chromic acid is a strong oxidizer, which is why it takes this carbon, it removes its hydrogens, and it increases bonds to oxygen. Strong oxidizer. Chromic acid is nice in that you can run this reaction in a pretty reasonable amount of time. The other reagent that gets this done is potassium permanganate, which needs to be run hot for about 24 hours. So one reagent, you can get it done in a day's work. The other reagent, it's going to take an entire day to run the reaction. So when you see this reaction in my class, you'll often see it with chromic acid rather than potassium permanganate. And there's one other thing I want to point out. Potassium permanganate typically run in acidic conditions. But it's not always written that it's run in acidic conditions. All right. And just wanted to point out, both of these reagents are considered oxidizers. Let's look at a more interesting example. I want to take us back to this bicyclic structure that we were analyzing before. And I'm going to mix it with chromic acid. And we'll demonstrate why it's appropriately called oxidative cleavage. I'm curious what you think will happen in this reaction. Do you think the product will have a carboxylic acid, two carboxylic acids, a ketone, two ketones, alcohols? Based on our first one, we saw that all the hydrogens got removed and the carbon was completely oxidized. But now that that carbon is bonded to other carbons, does the same thing happen? What's your intuition? You've got it. This is going to make 1,2-dibenzene carboxylic acid, or dibenzoic acid, which I think is simply referred to as phthalic acid. Notice what happened to the other carbons. They got cleaved. And we're not interested in what happens to those. So we're just going to say that this produces some byproducts. And this is really challenging. Textbooks don't answer what happens to the other carbons. The internet doesn't have a lot of resources on what happens to the other carbons. The best information I've gotten is that the rest of the carbons are probably just charred. They also get digested and oxidized.
So this is aromatic ozonolysis?
It's not ozonolysis, obviously, because we're not using ozone. But ozonolysis is also oxidative cleavage. And it's similar, but rather than calling it aromatic oxidative cleavage, I think it'd be better for us to call it benzylic oxidative cleavage, because it's not happening to the double bonds on the aromatic ring. And I think by calling it aromatic oxidative cleavage, you kind of get that misconception. Instead, it would be better to call it benzylic oxidative cleavage. Fair? A requirement for this reaction. If there is no benzylic hydrogen, then there is no reaction. So here we take para-tert-butyl isopropyl benzene. We mix it with, I think that's Jones' reagent, but I honestly couldn't tell you. Don't care. Guys, sorry, I shouldn't say that. Anyways, one of those positions has a benzylic hydrogen. The other position doesn't have a benzylic hydrogen. So my product is para-tert-butyl benzoic acid. Don't trust a guy who can't draw his tert-butyl group twice in a row. Interesting. So why does it require a benzylic hydrogen? Why can't these strong oxidizing reagents just get at that carbon and start doing stuff? Well, oxidation involves typically one of two things, and/or removal of hydrogen atoms and increased bonds to oxygen, sometimes combination of the two. In this case, our oxidizers, one of those oxygen atoms binds to a hydrogen. If there's no hydrogen for the oxygen to bind to, it can't break any of the other bonds. It can only break a bond to one of those hydrogens. After that oxygen from the oxidizer removes the hydrogen, it leaves behind an intermediate that is conjugated to the aromatic ring and stabilized, which is why on tert-butyl, the oxidizer never oxidizes any of these methyl groups out here. If those methyl groups reacted with the oxidizer, the intermediate that they form is not conjugated to the ring, it's not stabilized by the ring, and so the reaction is not energetically preferred, it doesn't proceed. So, kind of useful, we can remove those hydrogens and we won't cleave that position. Okay. The next reaction that we'll look at is the opposite. Instead of oxidation of those benzylic carbons, we're going to look at reduction. Actually, instead of saying reduction of benzylic acyl groups, we're actually just going to say reduction of acyl groups. I do have a complaint about the textbook. The textbook introduces this reaction in this chapter, in this section on benzylic reactions, but this reaction does not require a benzylic position. The reactions that we're going to see can be done with or without the conjugation of an aromatic ring. So it's misleading. The textbook introduces it in this unit as if it requires the aromatic ring, but it doesn't. So reduction rather than oxidation means we're going to take aldehydes or ketones. And once again, there are two different reagent pathways that we can take that get us to the same product. Small caveat that I want to put. How many of you know what acyl means? Right, that's what I thought. So, do you guys remember that I've been kind of pointing out the acetyl group, which is that carbonyl plus one carbon? Acyl is related to acetyl in the same way that aryl is related to aromatic. So acyl implies carbonyl group, not necessarily carbonyl with one carbon. So acyl group here means carbonyl group. But more specifically, the acyl groups that this reaction proceeds with are only ketones and aldehydes. We will not see these reactions have any effect on benzoic acid, for example, or on amides or on esters. So the reduction of acyl groups, maybe we could just rewrite it and say reduction of ketones and aldehydes, because that's what these reagents will selectively do. One of the reactions is called the Wolff-Kishner reduction. This is where we take hydrazine in basic conditions, KOH, with heat. So hydrazine is this reagent, H2N, NH2. And I like to spell it out that way rather than to spell it as N2H4, because writing hydrazine this way tells you a little bit about what each thing will do. N2 is going to be a byproduct. This reaction is going to release nitrogen gas. That's your first indicator that the hydrogens are playing a major role in the reaction. Two of those hydrogens will be given to the oxygen. Whether that oxygen is an aldehyde or a ketone doesn't matter. And when two hydrogens are given to oxygen, what do you get? Water. So water will be another byproduct here. What then will the other two hydrogens do? Well, those other two hydrogens are given to whatever carbonyl carbon you have to replace the two bonds to the oxygen. If you have a ketone, two bonds to oxygen are removed, two bonds to hydrogen are added in. If you have an aldehyde, two bonds to oxygen are removed, two bonds to hydrogen are added in. And that is the in case you are interested in looking it up, Wolf is spelt with 2 F's. Wolff-Kishner reduction. The other reduction is the Clemenson reduction. And I think I've spelled that right. It's all E's. There might be 2 S's. Always forget. Clemenson reduction does the exact same thing, but uses different reagents. Here the reagents are zinc mercury with hydrochloric acid. So the zinc mercury is I believe the term is amalgam. It's a mixture of those metals. One thing that we know about zinc is that it oxidizes very easily. It gives away its electrons, it's a good reducing agent, and it bonds to oxygen, which means one of the byproducts here is actually zinc oxide. So the oxygen from the aldehyde or ketone is pulled away with the zinc. The hydrochloric acid is the hydrogen source. 1 equivalence of HCl per bond to oxygen that needs to be removed. All right? So to give you some context, this reaction does not require being benzylic, and I'll demonstrate that for you here. Let's use the Wolff-Kishner reduction. Oops. Didn't actually reduce it. What functional groups are there in the starting material?
Ketone and aldehyde.
Right. And if we describe it a little bit more, we can say a benzylic ketone and a non-benzylic aldehyde. We could also say a conjugated ketone. It's conjugated to the aromatic ring. There's an uninterrupted series of p orbitals. And a non-conjugated aldehyde. And what functional groups are in the product? Just the alkane and the aromatic ring. So those acyl groups have been reduced to alkane. This is an important framework. This is a way that I'd like you to think about changes in reactions. What functional group changes do we observe? Carbonyls to alkanes. That's unique. We're not going from carbonyls to alcohols. That's a reaction we'll see later in the semester. We're going from carbonyl directly to alkane. Pretty useful. And it's going to come back up in our next chapter as well. This is a good time for us to take a break. So why don't you guys get up and move around and get your blood flowing again. And in the meantime, I'm going to put up some practice problems where we can predict a starting material, predict a reagent, predict a product. And then I think I'll try to do a multi-step synthesis as well, where we can try to incorporate these reactions together. Sound good? Great. my Ocon 1 class gave me some feedback on their unit tests too. And they said, one of the guys said, I went to take my second attempt at part A. He was like, I kind of hated it and kind of loved it at the same time. He was like, I forgot that you told us the second attempt would draw different questions from the same bank. So I got in there and realized they weren't all the same question, and I got really upset because I thought I was just going to blow through it and put all the right answers down. And then he was like, but then I could tell that they were quizzing me on the exact same concept. So now I could really prove to myself that I do understand this concept without just putting in the answer for the one I already got wrong and know that I studied and got right. It's like, good. That's a good point, yeah. So you guys are going to run into that too. I know you felt it already with part A on this first one, but as we get into new material, you're going to see it. Like things you're really learning for the first time, and you'll be challenged. But hopefully that challenge makes you feel like you have mastered it. Fingers crossed. You solve them in your head first, though? Yep. Yeah. Sure. Mm-hmm.
3 steps, right?
Yes. Yeah. Now, well, the arrows don't necessarily tell you how many steps. Having multiple arrows just says multiple steps. That's all. You could do it in, I see you've done it in 3. You could do it in 4. You could do it in 10. So the number of arrows doesn't always mean the number of steps. Now, I'm not quite sure that that's true, that it's anti-Markov. The other thing is I would like to see a reagent, kind of like you've got these reagents. I'd like to see a compound that could run the reaction. And lastly, this one, I think it would be important to add hydrochloric acid, since that's where the hydrogen source comes from. Yeah, that's great. Actually, we're gonna start with these. It just means multiple steps, not even necessarily 3 steps, but more than 1 step. So you can see these first two are obviously just one step is happening, one change is occurring. That's good. Yep. That worked. Absolutely. Good work. So just to clarify, I wasn't needing to tell you that it needs 3 steps. I wasn't meaning to tell you it needs 3 steps, but you can solve it in 3 reactions. You could solve it in 4. I don't think you could solve it in 2. And I want you guys to work on it for just a couple more minutes, and then I'm going to kind of give you a nudge and have you collaborate as well. So if you don't feel like you can solve it, get as many of your thoughts down as you can. All right, let's answer these first 2 problems. And then I'll give you some tips and have you work together. Is there only one correct answer for this first reaction? Is there only one starting material that can react with these reagents and form this product? What do we know about this reaction? It's a reduction reaction. So we know that the starting material has all of those carbons. No carbons are gained or lost in this reaction. But we know that the starting material also has carbonyls. Are there any aldehydes? Could the starting material have an aldehyde? Since there's no carbons gained or lost in this reduction reaction, none of those positions work well to be an aldehyde. An aldehyde is a terminal carbon, only bonded to one other carbon. And every carbon in this structure is bonded to at least 2 other carbons. So there's no aldehyde possibility for a starting material. And the ketones can't go anywhere on the aromatic ring. If you put a double bonded ketone, take a look at our homepage of the course. If you put a ketone onto an aromatic ring, it loses its aromaticity because, I'm glad I pointed it out then, because it takes up some of that bonding character. So I could have a ketone that is directly benzylic. That would be a correct answer. I could have 2 ketones that are directly benzylic. That would be a correct answer. I could also have 1 or 2 ketones that are not benzylic, that are further away from the benzene ring. It could be one of those positions, it could be both of those positions. And this molecule probably doesn't exist, but it could be all 4 positions. There's no way to know. But the idea here is, if this is your target molecule, what structure can you start with? There's a plethora of options. There's no one right answer in this case. There's a lot of ways we could start. In this reaction, we can see that the ring on the right gets cleaved. 2 of those carbons are lost. The ring on the left, no reaction. So first of all, the change is from alkane to carboxylic acid. That's a strong oxidizing reaction. So there are 2 correct answers, chromic acid or potassium permanganate. Either one of those would get the job done. And I noticed some of you used potassium permanganate and then added hot in 24. That's great. Ultimately, I would accept it if all you put was potassium permanganate, since that's the main part of the reaction. Can somebody explain to me why the ring on the left doesn't go through any cleavage?
There's no available hydrogen.
More specifically,
No benzylic.
there are no available benzylic hydrogens. Exactly. Both of the benzylic positions attached directly to the ring are quaternary carbons. They're bonded to 4 other carbons. So these groups cannot go through oxidative cleavage. Cool. All right. I'm going to forget this if I don't point it out now, so I want to draw your attention to something. Monday, we have part 2 of our analysis of an organic compound due. This is something I should have pointed out last week so that you could get started on it after we finish learning about spectroscopy. Part 2 is to take your molecule and identify all of the bond types that are present and predict where they would absorb. That means that you will need to use the correlation table. I do not expect you to do this analysis without the correlation table. And once again, it's going to be pass-fail. So either you get all of the bond types and you get a point, or you miss one or more of the bond types, or have them mislabeled, or don't have the correct range. And I give you a 0, and I ask you to go and find those corrections and resubmit it. So the earlier you start on it, the earlier you can submit, and if you've missed anything, the more time you have to continue working on it and resubmitting. Of course, I'm not taking late points for these, so submit as often, as late as needed to get that point, right? This is a mastery-based assignment. I want you guys to feel like you do know how to use that correlation table. I think it's going to set you up for success on the midterm, because there may be 1 or 2 graded questions on IR on the midterm, but there's almost always bonus problems on those exams that incorporate spectroscopy. Shouldn't take too long, but try to find time to squeeze it in. Okay, looking at our multi-step synthesis, I gave you guys that clue that we could do it in 3 steps. You could do it in more, but oftentimes we're looking for the most efficient multi-step synthesis possible. Do you guys remember the tips that I gave you on multi-step synthesis?
Start from the beginning and the end.
Yeah, one of them is work forward and backwards. Don't lock yourself in thinking that you have to take the starting material and figure out how to change it to get to the final product. Sometimes you can take the final product and figure out what came before it, similar to what we did here. I can figure out what a precursor possibility is. Do you guys remember the others? One of them is map your carbons. Now I put this one first and foremost Because it's an important idea to know whether you're gaining carbons or losing carbons. And in this case, I think it's pretty obvious. No carbons are gained, no carbons are lost. And the last point is to brainstorm. In order to brainstorm, you have to first identify the functional groups that are there. And then you have to review your notes. I saw a lot of you guys scrolling through to look at the reactions we just covered. Figure out what reactions that we have learned that take advantage of those functional groups or that form those functional groups. So I want you guys to spend maybe another 5 minutes brainstorming together and working forward and backwards. I know some of you have already identified a good synthetic route. So rather than just handing it to your classmates, I want you to maybe walk them through your process or even try to get them to agree with your process, yeah? So let's spend maybe 5-7 minutes doing this in groups of like 2 or 3. I don't think it's possible to do groups of 2 or 3. 3 or 4. If you want to do it all together, I'm happy to let you do that too. Have at it. This would work great. Water would work. Water and heat would work. Hydroxide and heat maybe is better. Tert-butoxide works as well, but we'll actually do it a little bit differently. Small T, big B, and then U, O. So without the oxygen, you're kind of just applying a tert-butyl carbon chain. So B-U-O. There you go. And then a little negative sign to indicate that it's an anion. There you go. That would do it too. But if I use that one already. That's true. Mm-hmm. The reason we need heat hydroxide is because it's also a good nucleophile. And at that secondary position, you risk substituting rather than eliminating. So we want to make sure that we prioritize elimination. In all honesty, on the midterm, I pay less attention to whether you indicated so if you gave me something like sulfuric acid, a lot of times I have questions like this, and when I'm looking to see is your understanding. I understand that sulfuric acid is the catalyst for elimination of alcohol. So those are typically 2 points. I probably would have taken 1 point off. You get a point because I see that you recognized running elimination. You lost a point because sulfuric acid doesn't eliminate alcohol.
come here, and then come here, and then it goes all the way around, which anything stiff on the resonance is usually the most stable way, because resonance
Yeah.
really helps.
Why would you
Since-
use one over the other?
Since
Is
this round really what forms there, because
access.
if it were to
So you
form-
run into our chemistry stock room, we've got a ton of sodium
if it were
hydroxide.
to form
I don't think we have any
here,
proof.
it wouldn't be able to reach that
So
resonance.
you
It's not,
probably would want to run.
it's not in opposition, yeah, and so that's why it would be.
Now, the other thing you
opposition
could
is
do,
the most stable
If
route.
some of it ends up doing substitution, you could try to isolate the alkene that forms from the alcohol that forms. And then you could mix that alcohol with sulfuric acid
And then you can
and run
use
elimination on the alcohol.
strong
And then you could get a larger conversion of your product. That's kind of your like real life application of it, but good work, guys. I overheard you guys too. Good thought process. Jenny, you're following what
Yeah, that makes sense.
her brainstorming.
I hate synthesis, but I think it's better idea.
Well, you've got to identify the functional groups, and then that will help you brainstorm. What can I do with this functional group?
What do I need to?
What do I need to do to form this functional group?
Okay.
Yeah, that's good. That makes sense.
You're like the last one. We know the mechanism.
Yeah.
So I want to hear from you guys about your brainstorming. At your first approach, did you do any brainstorming? Did you say, I've got this functional group that I'm starting with or forming, here's something I can do to react with that group or to form that group? Caesar?
Well, I just saw where we were going. I don't think there's any direct way there. You said it was three steps, but you found it now. So I just thought, well, I gotta eliminate this and everything now. So
This.
now
I've got to do elimination.
Yeah.
Yeah, so that was part of your brainstorming is, I've got to do elimination. And how many different ways are there to do elimination? There's a few. Yeah, what if you have an alcohol elimination? You'll want to use sulfuric acid. But if you have an alkyl halide elimination, you want to use a base and maybe a base with heat. So is that kind of what you said first was, I know I've got something that needs to be eliminated. And in that brainstorming, did you have an idea about where along this carbon chain it might be?
yeah, kind of. Because I mean, I saw where the double bond is, so it has to be either one of those two carbons.
It's got to be at one of these two positions.
Right.
So maybe with our brainstorming, we still leave a blank there. I'm not sure which position I'm going to need a leaving group to be on. Although, if you're trying to work forward and backwards, you can recognize that of those two positions that are kind of going through this change, only one of them has a functional group that can also go through change. So maybe it's on that position, but maybe it's not, because we're not sure what else we need to do yet. All right, what other brainstorming ideas came to you?
I just kind of thought with that ketone that I needed to get rid of the oxygen double bond because there's no way for that to like be eliminated and turn into that other double bond that we know of. And so I thought we have to get rid of that and put something on it that could eliminate and get that double bond.
Good. So I've got to get rid of it, and how many ways have we seen to get rid of that double bond? Two.
Yeah.
Yeah, two ways that are identical to each other, right? Just different reagents. So this is either the Wolff-Kishner reduction or the Clemenson reduction. But either way, we don't have to guess about what product that's going to make, do we? We can actually work forward pretty easily to say alkane. I go from a ketone to an alkane. Great. So now I've got this idea where I've got an alkane. I need to get a leaving group on there so that I can do elimination. And this is the beauty of working forward and backwards, is a lot of times you kind of meet in the middle and you can figure out how those two directions need to connect. So is there a way to go from alkane to functionality? We saw that we could do oxidation, oxidative cleavage. I could take the benzylic carbon and I could turn it into benzoic acid, which is going to remove those other two carbons, and benzoic acid is not a leaving group. So I think oxidative cleavage is out of the question. What else could we do? When you see an alkane, or in this case, I guess a benzylic alkane, one of the only reactions that should come to your mind is radical halogenation. That's pretty much the only way to take an alkane and give it functionality. Unless you've got enzymes. Enzymes are pretty fun molecular machines. So I could use NBS, I could use BR2, but Caesar, how am I going to know which position it goes to?
Because the benzylic carbon, that's the, what do you call that? It's the best position because it's going to be allylic. Is that right?
Benzylic. Allylic would be if it's just an alkene. Benzylic for our benzene ring. But you're right. At that benzylic position, the intermediate is most stabilized. So I know that my bromine will add selectively there, which is really useful because if it had added at, say, the primary carbon at the end, I would have had a harder time getting my alkene where I wanted it. So now I just need to fill in the reagents. I think here I'll use my Wolff-Kishner reduction because I like it. And in terms of elimination, can I use sulfuric acid? No, the sulfuric acid is going to do nothing with the alkyl halide. And I was talking with a group about this. On a unit test or on an exam, if you're solving a synthesis or filling in a reaction roadmap, then I like to give you partial credit for understanding what kind of step needs to happen, but I do take off partial credit for not having reagents that accomplish that goal. So here, putting sulfuric acid, I understand that you're trying to run an elimination, but it doesn't react with the alkyl halide. Instead, we'll need a base. There's one really good option. Tert butoxide. Don't need to run heat or anything. Tert butoxide is so big and bulky, it has a hard time bonding to that carbon. So rather than substituting, it's just going to steal a hydrogen. But I could also use something like hydroxide and heat. A smaller base, hydroxide or methoxide or ethoxide, smaller bases are going to require more heat so that we favor the elimination rather than substitution. All right. Before you guys leave today, I'd like to hear your muddiest point. What is it that you're going to leave here today and go back to continue reviewing as we finish up section 15 tomorrow and move into section 16 next week? All right, I'll meet you guys by the door, and with that,